Hello. In this video, we're going to start with looking at a basic algebra problem where we have two rational functions, 1 over x minus 2 plus 3 over x plus 1. And we want to combine them together into one rational function. Well, if I wanted to take these two functions and add them together, we're going to need to find a common denominator. And since this is already a simple enough problem where we can see all the factors of the denominator, we're going to multiply this x minus 2 by x plus 1 over x plus 1, because I want my denominator to be x minus 2 times x plus 1. So to get x minus 2 times x plus 1, I'll multiply by x plus 1. And for the 3 over x plus 1, to get the denominator of x plus 1 times x minus 2, I need to multiply by x minus 2. What I do to the denominator, I do to the numerator, to keep the balance, to keep the fractions balanced and keep them the same. So this line is the same as the line above it. Now, multiplying these fractions together, the first one, 1 times x plus 1, becomes x plus 1, and the denominator, x minus 2 times x plus 1, is x minus 2 times x plus 1. Now, 3 times x minus 2 is 3x minus 6, and the denominator is x minus 2 times x plus 1. Now we have two fractions with the same denominator, a common denominator, so we can add those numerators straight across. X plus 3x is 4x, and 1 minus 6 is 5. The denominator, I'm going to now multiply that out to get the quadratic. This would be x times x is x squared. Negative 2 times x is negative 2x. 1 times x is 1x. And negative 2 times 1 is negative 2. Simplifying this one more time, we'd have 4x plus 5 all over x squared minus x minus 2. So we get that 1 over x minus 2 plus 3 over x plus 1 is 4x plus 5 over x squared minus x minus 2. Great. Now, suppose we wanted to integrate this 4x minus 5. Said minus, I wrote a plus. Suppose we wanted to integrate this 4x minus 5 expression over x squared minus x minus 2. We could do some complicated u sub where we'd have to complete the square on the denominator and make a u sub, and there'd be a lot of steps. We could do it, but it will get complicated. However, based on the problem before, we know 4x minus 5 over x squared minus x minus 2 is the same as 1 over x minus 2 plus 3 over x plus 1. So this integral is the same as the integral of those original fractions we had. The original ones that were being combined, the 1 over x minus 2 and the 3 over x plus 1. Now, each of those is really easy to integrate. The first we would integrate, we essentially have a 1/x example, and the antiderivative of 1/x is the natural log. So we get the natural log of the absolute value of x minus 2 for the first antiderivative. And then the second antiderivative, the 3/x plus 1 with a basic u sub, will become 3 times the natural log of x plus 1. And now a plus c. And there we have the integral of 4x minus 5 over x squared minus x minus 2, with not a lot of work, except for the fact that we knew this equality. We knew this fraction on the left could break into the two fractions on the right. This introduces a strategy known as partial fraction decomposition. Partial fraction decomposition is an integration strategy where what we want to do is take a bigger rational and break it up into smaller fractions. So I will write out what I said. Take a bigger rational and break it up into smaller fractions. And what those smaller fractions will initially have is some unknown coefficients. We have some known ways we can break up fractions. First, when we break up the fraction, and we'll see this in several examples, every factor of the denominator of the rational gets a fraction. And I'm going to add a note here that says build the degrees. I will talk about what that means in a later example. But we're going to build up the degrees of these factors. Second thing is that the number of coefficients, these unknown coefficients we don't know, will match the denominator degree, or the degree of the denominator. And the last thing is when we have a linear factor, we're going to put a constant above the linear factor. And when we have an irreducible quadratic factor, we're going to put a linear above it. So we're going to cut down the degree by 1. We'll see again what this looks like. So above a irreducible quadratic, we're going to put a linear. So we want to break up this rational into smaller fractions, and the ways we're going to break up those smaller fractions are laid out here. Again, we'll look at examples. But once we have these smaller fractions, we can then solve for the unknown coefficients with some different strategies. And now, after we solve for the unknown coefficients, we have smaller fractions that we can integrate. So let's look at an example. The whole process in general is trying to take something bigger, like this 4x minus 5 over x squared minus x minus 2, and work backwards. So we're ultimately going to work backwards through this line to find these values. So that's the process we're going through. So let's look at this first example. We have 3 minus x over x cubed minus 4x squared minus 5x. We want to break this fraction, 3 minus x over x cubed minus 4x squared minus 5x, into smaller pieces. And it says every factor of the denominator will get a fraction. So I need to factor this denominator. So our partial fraction decomposition is going to say we have 3 minus x over x cubed minus 4x squared minus 5x. And factoring this denominator, first, everything has an x in it, so we're going to factor that out. X squared minus 4x minus 5. And x squared minus 4x minus 5 factors in to x minus 5 times x plus 1. And we can factor that denominator. So after we factored it, every factor is going to get a fraction. So our factors are x, x minus 5, and x plus 1. This means 3 minus x over x times x minus 5 times x plus 1 is equal to every factor gets a fraction. So there's going to be a fraction over x plus a fraction over x minus 5 plus a fraction over x plus 1. Every factor has a fraction. The second tip is to put a constant above the linear factors. All of these are linear. Their degree is 1. So over x, I'm going to put a linear, meaning I'm just going to put a single coefficient, a. Over x minus 5, I'm going to put a single coefficient, b. And over x plus 1, I'm going to put a single coefficient, c. I now have two fractions that are equal. And so I can multiply both sides by this common denominator. And when I do that, this is going to clear away all the fractions. When I multiply this left-hand side by x times x minus 5 times x plus 1, the whole denominator goes away, and I get 3 minus x. When I multiply a by x, when I multiply a over x by x times x minus 5 times x plus 1, the x's cancel. This x cancels with this x. So I end up with a times x minus 5 times x plus 1. When I take the b fraction, b over x minus 5, and I multiply it by x times x minus 5 times x plus 1, the x minus 5s will cancel, leaving us with b times x plus 1. And last, when I do the same for the c, the x plus 1s cancel. And we're left with x times x minus 5. From here, what we want to do is solve for these coefficients. And we'll see a few different strategies for how we solve for A, B, and C in some videos. This one, we're going to see the very quick strategy that when everything is a linear, and specifically a unique linear, we can solve for these very quickly. Because if we notice, when x equals 0, we get b times 0 times 0 plus 1. And we get c times 0 plus 0 times 0 minus 5. These two terms will go away when x is 0. Whereas 3 minus x will just be 3. X minus 5 is negative 5 when x equals 0. And x plus 1 is 1 when x equals 0. That means A equals dividing by negative 5 times 1, 3 over negative 5. And now we have A. We can repeat this process for B and C. So B, the factor that's missing is the x minus 5. When x equals 5, x minus 5 is 0. So that x minus 5 will go away to 0, and this x minus 5 will go away to 0, making these whole terms become 0. So since that whole thing is 0, the A times things is 0, and C times things is 0, we can plug in 5, and 3 minus 5 will equal B times 5 plus 1. Or negative 2 is equal to 5b times 5 times 6. So b times 30. Dividing by 30, we get b is equal to negative 2/30, or negative 1/15. We have the coefficient of b. And finally, c. What c's factor doesn't have is the x plus 1. So when x equals negative 1, the thing that would make x plus 1 0, we will get 3 minus a negative 1 equals a times negative 6 times 0 is all 0. Plus b times negative 1 times 0, because x is negative 1, is all 0. So that is 0, that is 0. And so we get c times negative 1 times negative 1 minus 5. 3 minus negative 1 is 4. Negative 1 minus 5 is negative 6 times a negative 1 is 6. See? So C equals 4/6 or 2/3. There are our coefficients A, B, and C. We said our partial fraction decomposition is going to break down into this A, B, C fraction. Those are what A, B, and C are. So going all the way back up to this top part, this partial fraction decomposition breaks down to be negative 3 over 5 times 1 over x. A is negative 3/5. Plus negative 1/15 times 1 over x minus 5 plus 2/3 times 1 over x plus 1. Because 2/3 is c. So we get these three fractions that are going to be a lot easier to integrate. So now after this partial fraction decomposition, I want to integrate 3 minus x over x cubed minus 4x squared minus 5x. So integrate 3 minus x over x cubed minus 4x squared minus 5x dx. This is the same as integrating negative 3/5 times 1 over x plus negative 1/15 times 1 over x minus 5 plus 2/3 times 1 over x plus 1. So there is what we want to integrate. The integral of negative 3/5 times 1 over x is negative 3/5 times the natural log of the absolute value of x. The antiderivative of negative 1/15 times 1 over x minus 5 is negative 1/15 natural log of x minus 5. And the antiderivative of 2/3 over times 1 over x plus 1 is 2/3 the natural log of x plus 1 plus c. So once we do this partial fraction decomposition, the integration is really quick. But we can break these fractions down into smaller pieces to make our integral something easier to do. So we get that the integral of 3 minus x over x cubed minus 4x squared minus 5x, breaking it down into these smaller fractions, becomes this negative 3/5 natural log of absolute value of x plus negative 1/15 natural log of x minus 5 plus 2/3 natural log of the absolute value of x plus 1 plus c. We will take a look at more examples in the next videos.